Okay, welcome to lecture 62. We have been discussing about the general orbit perturbation theory. So, if in that context till now we have looked into how the due to the extra potential term or the extra perturbation term, the equation will look like. Now, actually we have to find out the terms. If you remember that we have written r double dot equal to minus del u plus r, and thereafter also in the force term we have written this equation. So, all these things till now we have worked out. So, today we will discuss about the potential of a body of arbitrary shape, and using this, then this will be our first step to know how the perturbation term. Already we have looked that mathematically how it is arising in the but till now we have looked into the f form, but say if we have this term minus del r. So, this del r equal to f, okay, and we want to know actually how does or what will be the feature of this function f here or the force f here, okay, what are the terms involved in that. So, this we need to derive. So, we will do it for today for oblate sphere, means you have a sphere, but it is a here say the x and y dimension are the I x x and I y y. The moment of inertia about the x axis and the y axis it is the same, but I z z it is not the same. So, this that is I x x equal to I y y, and this is not equal to I z z. So, this particular part we are going to look through the derivation for a body of an arbitrary shape. First we will write the equation, and thereafter we will take this particular case and work out how this term will appear. Okay. But before that, one correction from the last time, that we have written the omega equation in which we dropped out one term, and again there was a small error in that particular term. So, I will correct that. Okay. So, because we are going little fast, so we have less time. So, it is likely that some of the typing error creeps in. F theta minus r sin u, and this is cot I. Instead of cot I, last time it was written as cos I. Okay. Only once the lecture was over, so I noticed that. So, this term last time it was written as cos I, which is not correct. This is the correct term here, okay, and this multiplied by f a. Okay. So, with this now we start with our main topic of discussion today. Okay. So, look into this configurant. Let us first consider that there are two masses m and m 1. Okay. You can show by a small letter or capital letter, it does not matter. So, two particles two particles of masses m 1 and m located at P 1, which is described by vector r 1 and P described by vector r respectively. Now, consider that this mass m is small, okay, as compared to. So, m is much smaller than m 1. So, under this condition, so we can get the potential due to the main body or the particle m 1. Okay. So, potential at P due to m 1 can be written using u equal to minus g times m 1 divided by r 1, okay, where r 1 is equal to magnitude of vector r 1. R 1 equal to r minus r 1. Okay, so, these are the informations available to us, and as usual you know that if you want to write the equation of motion in the reference frame, the inertial reference frame. So, we can write m 1 times r 1 double dot, this is the motion of particle capital which is given by P, P 1 here, we have to, this is P 1. So, m 1 times r 1 double dot, this will be equal to m times m 1 g divided by r 1 cube times r 1, and sign will be plus because the force is directed along r 1 direction. Similarly, for the small mass we can write this as m r double dot, this equal to minus m m 1 g divided by r 1 cube. So, there is no problem in this, we have done it numerous times. So, this is the same thing. Okay. So, using this, then the equation of motion for the smaller mass can be written as, if we use this, so see here m is, this is multiplied by m r double dot, and then on the right hand side what are the terms which will appear. So, we know that from our earlier experience or the or our earlier discussion, we have written this as minus m times del u. Okay. So, you will get this quantity, this expression from here. Okay. So, thus the motion of mass m under the action of or the gravitational acceleration of mass m 1 can be written as shown above. Now, in the case there are number of masses, there are many small particles, then the potential at P can be written as u equal to, or we can write here just like the u1, okay, to represent it better. So, we will write it as u1. So, here we will write as ui, and u will indicate as I equal to 1 to n, the summation over n number of particles. So, potential due to n number of particles. So, this is minus g r I. There we have used r 1 for this notation. So, for better representation, instead of using capital R, we will use the small r. So, this is then the potential due to a number of particles, and therefore, then the equation of motion for the small mass, this can be written as, if we go back and use this equation. So, this is m times del u. So, minus m times del u. Here this quantity we have written as 1, where u 1 is defined like this. So, the format of the equation does not change, it remains the same. Okay. So, this constitutes our basic principle, how the potential at a point P can be worked out. Now, if the body is, or either if instead of a body, instead of particles, discrete particles, instead of discrete particles, if we have a finite size solid body under whose action particle P of mass m is moving, then the above summation needs to be replaced by integration sign. So, now we are talking about here we have a body of arbitrary shape, and there may be a elementary mass located in this. Here it is shown very big, but it is infinitesimally small. We can assume the distance from here to here, we can show it by rho. This is the vector to this point, and then of course, we have the point here P, whose radius vector we can show as r. This distance we can write as P. So, find the potential at P. So, what will be the potential at that point? So, let us assume that this mass is dm, okay, elementary mass, and based on that then we calculate the potential here and then we integrate over the whole body. So, du is then minus g times dm divided by the distance p, which is in this case is nothing but we have written this, we can write as q, this point, and this point as O. This point we can write as q. Okay, so, PQ distance is P magnitude equal to P, this is nothing but the distance PQ. Okay, so, this gives us potential, and what is the value for the P? So, for the P already we have written P is the vector r minus rho, and if we take dot product of with the self. So, this becomes P a square So, throughout we have taken the vector approach. This is not the only way of doing, the scalar approach is also there, and many of the books may be discussing this matter in some different way, but this is one of the most elegant way of doing the things. So, this becomes then r square minus 2 r times rho, and the angle between these two, let us say we write this as theta or phi, whichever the notation you prefer. Let us say this is phi, this angle is phi here. So, this is phi plus rho square, and if we take rho r square common. So, this will be 1 minus two rho by r cos phi and therefore, potential at P due to the elementary mass, this can be written as minus g dm divided by P is nothing but r 1 minus 2 rho cos phi and if we have to find out the potential due to the whole body. So, we just need to sum it over the whole body, and then r is independent of the integration over the body, because it depends, the integration just depends on the mass where the rho will factor, okay, and therefore, we can write this as 1 minus 2 rho by r cos phi plus rho by r square to the power 1 by 2. We can write it this way. Okay, where x has nothing to do with, or we can use some other notation maybe. let us say we write here W, where W is nothing but the quantity from this place to this place. And this expression has got a standard representation in mathematics, but we will do it by expanding here rather than just going to that first. Still let us write this, then u becomes minus g by r, it can be represented as okay. And what is dm? Dm is also a function of say if the mass is, the density is not uniform. So, this will the mass of this is small mass dm, here elementary volume will be taking. So, this will depend on that the density also. Okay. So, but this is not we are featuring here, we go here in a simple way. But of course, in the case of if you want to have like you have a body where the density from one place to another place is differing, and if you are ready to model, take the mathematical complexity into account, and then you have the observation data available. So, it is possible that you can say where the density is more and where the density is less. This has happened in the case of the Apollo satellite. So, Apollo satellite and still it is going on those work. The many of the observation data for the lunar satellite. So, from there the they were reduced, and then the perturbation acceleration were worked out, and using that it was shown that some of the places where the mass may be more dense. Okay. So, those kind of analysis it is possible. Okay. So, you will find it interesting this topic as we progress. So, 1 by 1 plus x under root what we have written. So, this whole thing except dm, it can be represented in a series form, like this is p n cos phi times rho by r to the power n dm, where p n is called the Legendre polynomial. So, this is one of the representation, and this representation if we reduce in terms of Legendre function. So, there the spherical harmonics they come into picture. This is another way of describing the things, but the approach right now we are taking it is a little simpler. Okay. So, if we take a point close to the a point P close to the body or the main body, then the rho by r will be of the range around 1, and in that case, in this case the series shown over converges very slowly. And then modeling u in terms of this series requires large number of terms. So, in the case of the moon, So, once the lunar gravity modeling is done, so at that time there are lakhs of terms. From this place it can be expanded. Okay. Rather than expressing here in this format, it is expressed in terms of Legendre function, okay, where the spherical harmonics they come into picture. Okay. And in that, beside the main gravity term which we write as g m by r, many other terms they appear, okay, lakhs of other terms will appear, and using that then the lunar gravity modeling or the potential due to the moon or the perturbation arising on the lunar satellite due to the moon. So, they are worked out. So, this is because of this reason. So, if you are in the nearby regions where the rho by r is nearly equal to 1. So, in this case this series converges very slowly, okay, and then the modeling of u in terms of this series requires a large number of terms. So, it may be in terms of lakhs. But if rho by r this is much greater than much less than 1, means r is quite large as compared to rho, much less than 1, then the above series converges fast and only a few terms will suffice in such cases. That is, all higher order terms can be neglected. Okay, so, this 1 by we have written once we go back here, this part already we have written here, p equal to the quantity in this place. And this we are going to work out. So, using the binomial expansion we can work it out. So, this is the equation that we are having, and if we expand it to a few terms, this is g by r here. So, 1 minus 1 by 2 rho by r cos phi whole square, then plus minus 1 by 2 minus 3 by 2. Okay. So, this way there will be an infinite number of terms in this expansion, and this expansion is not very difficult to work out. Using the Taylor series you can do the expansion of any function. This kind of function is very easy to do it, and this is a very standard equation available in the books. Minus 2 rho by r cos phi plus and so on, the higher order terms. 1 plus, now if we break the bracket here. So, this becomes rho by r cos phi plus here minus sign minus 1 by 2 rho by r square plus from this place we have 2 to 4 8 3 by 8 times minus 2 rho by r cos phi whole square dm. Plus 3 by 8, and if we square it, so this becomes 4 rho square divided by r square cos square phi plus rho to the power 4 r to the power 4 minus 2 into 2 4 rho, this becomes rho cube by r cube cos phi. So, we ignore the higher order terms, means the third order and the fourth the third degree and the fourth degree terms will be ignoring, and if we do that, cos phi. So, that means only this term and this term we are then accounting. So, then this becomes minus rho square by 2 r square, and from here we get plus 3 by 2 3 by 2 and then rho square by r square cos square phi. So, here we are neglecting higher order term. Rho square by r square we take outside and 2 also from the denominator. So, this gets reduced to 3 cos square phi minus 1, 3 cos square phi Okay, now of course, then we can write this as minus g dm by r minus g by r square rho cos phi dm minus g by 2 r cube rho square this we can represent as u equal to u 0 plus u 1 plus u 2. So, if we take higher order terms, then u can be shown as u 0 plus u 1 plus u 2 plus u 3 and so on. And if you remember, the term we have written minus g by r u equal to in terms of the Legendre polynomial from 0 to n, this summation was, and the p n cos phi, and then we had rho by r to the power n d m. This is what we have written. So, this implies that the first term is equivalent to, if we now expand it. So, this will be p 0 cos phi and d m minus g by r summation we are breaking the summation. So, this is p 1 cos phi rho by r d m and plus so on. So, immediately you can see that this term is corresponding to here u 0, this term is corresponding to u 1, and similarly the next term will correspond to u 2 and so on. So, these two are the same, okay, and this is the way it is expanded. So, this is one of the approach, but there is another approach in terms of the Legendre function, okay, and that is done where we get in terms of the spherical harmonics. If time permits, I will take that up, or otherwise I will just give you the supplementary material on that particular topic, because already we have crossed the number of lectures and we have many other things to cover. Okay. So, but this is the idea involved in working with this problem. This is the basic idea. Here, instead of writing 2 here in this place, we can also write it as, it is a little more convenient to represent, because this is going like this way. So, immediately you can see that what does it mean if we are expanding. So, the second term, the third term will appear here. So, this is corresponding to u 2. So, that means the r cube here, the term, let us say that I expand it one more term here and write. So, that you also get the idea. So, the next term will be minus g by this rho by r, we can take it outside, r we can take outside. So, rho will come here and r we can take out from this place and write here g by r square. So, you can see that g by r square appearing here, this is also appearing here in this place, and rest inside is rho p 1 cos phi and d m multiplied by d m minus g. Similarly, here in this place, if we expand it, so this will be g and then p 2 cos phi rho square d m, r square we can take it outside and this becomes r cube. So, immediately from this place we can refer that p 0 cos phi, from this place immediately you can see this quantity is equal to 1. Okay. From here we can guess that this quantity will be p 0 cos phi, this will be equal to 3 by 2 cos square phi minus 1 by 2, and similarly this is p 1, not p 0, this is p 2 cos phi, p 2 cos phi and p 1 cos phi. From this place we see that this is simply cos phi. So, this way the series can be, if we are able to handle that much of mathematics. So, we can see from this place how this works, but in mathematics this Legendre polynomial, it is the well researched and well documented. So, any book you can pick up and the books like the Kreyszig on engineering mathematics. So, you can refer to those books and you will get these materials. So, we stop here and then we will continue in the next lecture. Thank you very much.